Sam, is that you? Are you Sam
Hi
Senchal?
guys, can you hear me?
Yeah, I can hear you.
Okay, one moment. I'm just getting video on.
Oh yeah, no worries.
Hi, how are you?
Hello, nice to meet you.
Nice to meet you too. Um, should I share the screen with the presentation?
Yeah, try to share it just, before starting, checking that everything is working fine.
Okay, let's see. One moment. Hold on, I just need to sign back into the meeting. Give me a moment.
Yeah, okay, no worries. Okay, nice.
Have
We
you
can
have you
see that.
have
Yeah.
you got it in full screen now?
Uh, yeah, now it's full screen.
Okay, brilliant. Hold on one
Perfect.
moment. Let me just.
Where are you based, by the way?
I'm in London. Hold
In
on.
London. Okay, nice.
Is it still full screen on your side?
Now I'm seeing yeah, I mean, I'm seeing like the your desktop basically with the
Okay, hold on.
browser in it.
Sorry, let me just see if I can get this to work properly.
Yeah, like a minute ago, I was like, it was like full
Hold on
screen.
one. Sorry, apologies.
That's
Not
okay.
not greatly technical with this stuff.
That's completely fine. Yeah, now it's full screen. Yep.
Brilliant. Um, one moment. Just grab my notes.
Yeah, just let me know when you're ready, and I see
Oh,
Carl around, so we can start whenever
um,
you're ready for it.
yes. Oh, sorry. Did that go off? Have you got my screen still?
But now we lost the full
Okay,
screen.
sorry. It's there you go. Okay, there you go. Sorry, guys. Apologies for the
Yeah,
delay.
now.
Um,
That's all right. Yeah.
so I'll kick this off, I guess. Thanks so much for having me. My name's Sam Senchal. I'm an independent researcher, loosely affiliated with the Wolfram Institute. So all of my research, because I use their base language, is typically run by some people there before I put it out and reviewed and critted pretty hard. And I've spent the last sort of 18 months working on extensions to observer theory within the context of the Ruliad. It's observer theory is part of how the Wolfram Physics project works. To get any sort of result from his gigantic infinite hypergraph, you must sample it with an observer that has a few properties, and those properties are boundedness, persistence, and relevance. And really, the motivation is to basically see what impact and sort of map the cartography of an observer, because I think compared to most things that I come across in the sciences, it's quite underdetermined. You know, typically you get definitions that are tautological, or you get measurement definitions which are very narrow. And here I'm trying within sort of the categoric framework of the Ruliad to map what those invariants are for an observer. I guess it comes down to sort of a couple of basic questions that are very old, which is, if reality requires observation to be understood, what is an observer, what's its formal properties, and what sort of constraints does it operate under? And then what are the impacts of those constraints when you push it through physics, biology, chemistry, memetics, and how things are organized? Is there universal patternation to this? And I think the thing that I found is quite surprising. I presented sort of a more formal version of the mathematics behind it to the Active Inference conference in November. And I think that the theory has a lot of direct connections to active inference, to things like integrated information theory, and to Michael Levin's work on basal cognition. And when I started looking at this research, it was a bit surprising, because this was really done as a sort of way to model a computational observer within the Ruliad, and it seems to extend to lots of other things, because when you model an observer computationally, you can start to say things with that about what things are doing in actual experiments with that language. And the neat thing for me is that you can connect with the Ruliad this sort of language of observation to physics, to math, to biology, in a way that's discrete, in a way that's non-probabilistic, that gives you some grounding. Okay, you have to buy that you can compute physics with Wolfram's model, but that is an unusual way to link things together by using the structure of the very sort of apparatus of computation to pull them into one picture. Let me see. Oops, sorry. So I just want to give you a bit of grounding. And again, if I'm going too slowly or too quickly, please tell me. So the diagram on the right is the types of computation that live in Stephen's Ruliad. You can think of it as sort of an limit object of every possible computational system, and computational state. It's not a physical object in the sense that like a particle is, but it really gives you the canvas for every rule-based universe, every set of conditions, every possible set of rules that you can work through. And I think the important thing to note here is that the Ruliad contains types of computation that go a bit beyond what we normally think about when we use a computer. So on the structural diagram, you can see on the right-hand side, the structural models are sort of static and timeless, and they're sort of mathematical models add time as a coordinate. We then, from Turing onwards, treat time as sort of progression of computational states. And then we get to multi-computation, which is many, many different threads of computation acting at the same time, computing at the same time, where the observer's taking a cut and selecting from that computational tree an end state. And so in the Wolfram physics project framework, an observer isn't an optional thing. There is no physics without one. It's not a philosophical afterthought of Stephen's. I think the mapping that's going on right now with the minimal model and sort of the extension that's built upon on top of it is to try and start formalizing and start getting to answers for things that can be testable and measurable within this framework for the observer. And here the major point, and I think it's one of the points that people in physics say to Stephen as well, if you have, or even someone like Max Tegmark, is if you have sort of this infinite multiverse, yeah, you've got everything, but it kind of tells you not very much. And so here we're trying to go, well, okay, if we set the boundaries of what an observer is within this model, and those boundaries are universal across all observers, can we now narrow this gigantic unwieldy structure down to something that outputs physics, that outputs the dynamics of evolution, and these are projects that are ongoing within the Wolfram Institute. And here, this is sort of theoretical scaffolding to some of those things to be tested and pushed against. So I want to look at sort of what the computational sort of boundaries of what I'm saying are here. And I think the important thing to note is in this sort of Ruliad construction of every possible computation, every single path is effectively a cause and effect process. And so the question that often comes up when I speak to chemists or biologists is, well, you've got an observer-based model, so there is, variable output based on the observer, so it's not useful and not predictive. And I think here, the thing that observer theory is doing is really saying what is variable and what is invariant within this type of structure. So here, what we've just tried to do is map that and say that the causal structures within the observers are independent, but the underlying structure of the possibility space is fixed, it's deterministic. And the computational samplings are therefore not invariant, but the relationships, the functors, the functors, the morphisms between states, and the laws that things sampling that object obey are invariant. So you get this sort of two layers of invariance, the bottom layer being the main object, the top layer being the composition of that object, but the middle and the result comes from the observer. And so this is really about mapping what is invariant within that structure, and therefore what do those invariances imply for behaviors of observers moving through time. So this will probably be pretty familiar to anyone working in FEP, but here an observer is a subsystem doing computations inside a persistent boundary. I think the thing to emphasize here is it's not just humans, it's not just brains, it's anything that has a boundary that separates inside from outside, that takes in information and updates its state and produces outputs. So Xerxes R.C. Waller and a few colleagues published a minimal observer model, and they define a tuple, an information object, where the observer takes an internal state space X, an input space, and an output space, and then takes actions. The transition function F updates those internal states, and an output function produces those actions, and that boundary separates an inside from an outside. And this will be familiar because it directly overlaps with FEP. So FEP here really thinks about that boundary in a Markovian process, and here we're just stating effectively a similar thing in computational language where we can get discrete answers based on measures that involve bits and that involve structured information. And one of the things that is being worked on right now is a measure for this space. So measures coming out of spaces like AI are now enabling discrete measures of bounded observers. And there was a paper by Finzi and a bunch of colleagues that produced a new measure called epiplexity, which is how we look at measuring how an observer samples information is being developed at the moment. I think the thing to really take away here is an observer effectively is like a filter, and they get a simplified version of the entire structure based on their limits, their boundedness, how much computational power they have access to, their persistence, how many state updates they last for, and the determination of relevance. How relevant is this thing that I'm sampling to my internal goals or the goals of that loop that I'm working through? This observer loop is what I just spoke about, but I think better to show it in a diagram. It's an H-stage loop, and again, will be familiar to people working with Markovian blankets, but effectively it's a similar thing, again, applied in computational language to work in the Ruliad. I think the thing to take away here is that the minimal conditions for this, so non-trivial sensing and non-trivial action, can be very empty or very full depending on the type of observer. So for observers like us, we get access to an enormous amount of information moment to moment. Just our eyes take in 10 to the 7 bits, and by the time we get to act, that's been compressed to roughly 50 bits in sort of the buffer of our conscious experience. And so this process and this loop is all about taking input, compressing it into a world model that's useful, that gives you more opportunity to exploit and explore, and then repeating that loop while continually updating your internal model. So again, lots and lots of overlap with ideas in surprise. Again, the statement here is that active inference is the right sort of gradient way of looking at things, and this is a method to make it discrete and measurable and computable in a way that perhaps probabilities aren't. Sorry. So I just want to talk about this diagram for a moment. This is talking about the field of observation for observers. So I want to point you to the larger dotted red box. So this is R0, or the observable Ruliad. And this is for an observer of a given class, how much of that computational possibility space, that latent space, they can potentially access given their minimum boundedness and their maximum persistence. So effectively like the limit space of potentiality for something like a human. The sort of pink box is the field of observation. So this is the affordance or the potential states that can be sampled given your current boundedness and your current persistence. And it also has where the judgment of relevance takes, where the observer makes a judgment of relevance over those states. So it's not ever sampling outside of that. And this is a function of the observer's computation through time. So over time, you expect that the field of observation grows towards the limit of the Ruliad over sort of n many or to the limit number of steps that observer can take. And so through time, this becomes important. The observers are effectively building a cognitive light cone, a bigger and bigger towards the limit based on their biology or the computational power of their brain. And the neat thing that humans do relative to other observers is we can artificially grow that through technology. So you get this step up when you get to us, you have this cone growing reasonably linearly with different objects, and then you get to us and we start to make things. And those things afford us more access to the observable Ruliad than anything else that's come before. And so the interactions of these limit objects, so the full limit observable Ruliad in the field, is how a lot of dynamics about prediction, about what is possible to predict, about state space enumerability and decision theory become quite relevant. And so some of the work I'm doing at the moment, apart from the measure paper, is a paper on decision theory based around these constraints, around whether you can measure the full space and seeing how that axiom impacts certain decision theory ideas. So I want to talk about some of the features of the formalism that are quite useful and when thinking about observers and how they interact. So the Ruliad in the observer theory paper is decomposed into domains or maps of different sizes in the easier way to think about it. Each map each domain is given by a certain amount of rule constraints. So for an informational object or an output to be part of a given domain, it must be subject to a certain amount of rules. And the domains that have more causal coverage, the bigger domains at the top, are subject to less rules for an object to be valid. That's useful in the context of distinguishing within the Ruliad between formal and efficient causation. And here we look at morphisms with increasing or decreasing amount of rule constraints to do that. We also look at a couple of technical points. So within the Ruliad's formalism, it's an infinite groupoid, which is a categorical object that enables topological closure. So every category that's closed in math has a terminal object. Here we're saying there's a terminal object in the category of the observable Ruliad, which means that the observer never has infinite regress when making a sampling. They can always effectively close a loop and get to an end answer. And here that is an inaccessible viewpoint because it's a point at infinity, a compactifying point in the formalism, and therefore that point at infinity is not reachable by bounded observers, even though they have reference to it within the structure. And so you see that the reason for that feature being included in the Ruliad's sort of formal model is because to import geometry, maths, and physics into a computational structure like the Ruliad that enables the Wolfram Physics project to derive or rediscover physics through that type of computational formalism, it must be closed in that way. Otherwise, an open category, you can't import the same the same type of geometry in there, and you can't do all the things that make it a sort of valid or edge physics theory in a way that's testable. And so by having that now imported to the observers as well, it lets you make statements that touch philosophy about how observers make decisions. And that, I think, is quite useful as we get on to parts of this about the implications of these sorts of ideas. I think to make it simple and to sort of make it intuitive to people, if you think of an observer like us and you think about what domains or what types of information we sample, we can split that into 4 layers. There are the very rule constrained physical layer, so particles bouncing off you, moving around. There's effectively a valuational layer, which anthropomorphically is kind of akin to an emotional layer. It's like goal direction. And then you have a symbolic layer. A symbolic layer is things like words, grammars, maths. And then you have what I call a minimally constrained layer, but it's intuitively akin to sort of an archetypal layer, like a layer where there are large causal objects that are impacting everything downstream of it. And because the map of the Ruliad is sort of integrated, it's a union joint map, the pre-images of lower domains exist in the higher domains or the bigger domains. So because it's all joined up, you can compose between those domains to create functions that say this physical mapping maps to this valuational mapping, maps to this symbolic mapping. And in fact, we're seeing that already in LLM representations. So in experiments like PRH, they're finding that there are natural activations that happen across models of certain sizes. And these activations work down in causal influence. And Eric Hoyle wrote a great paper on that, on causal emergence, which walks through how these sort of formal and efficient cause can work in both physics and in biology within the context of computation. So I just want to work now through some of the implications. I want to see really what falls out of this. And I think the first claim I want to make is that the observer formalism applies at every scale. A hydrogen atom can satisfy minimal observer criteria. It can absorb photons. It has non-trivial centering. It has internal states, and it produces non-trivial action. And here, for our boundary, we have the Bohr radius as a defined boundary, and its emissions alter its neighboring atoms, so you have feedback closure on the loop. It would be trivially an observer under this sort of formalism, not conscious or, in the way that a panpsychist would say, but it formally satisfies the criteria of an observer. It connects reasonably well to Michael Levin's program. His lab has shown that non-neural systems, so things like bioelectric networks, cells, and xenobots exhibit that goal-directed behavior. And these here in this interpretation are minimal observers implementing that loop without neurons. So the bioelectric code is sort of functioning as a slow update generative model where the cells are maintaining those voltage patterns that encode that morphology. And when you perturb it, and when you perturb those patterns, the tissue corrects towards the stored target. And here, that applying to you is active inference absent a brain. And so I find that to be, again, one of the overlaps where the tools of active inference and this idea of surprise, or this idea of, a high entropy state versus a low informational entropy state, are very useful in thinking about observers when adapting a model that's probabilistic to something discrete. We just talked about this, so I'll skip this, but this is just walking through all of the parts of the function and how an atom satisfies it. And then I just want to talk about symmetries in the Ruliad as things that effectively constrain information or lead to many more distinguishable states. So here we have in observer theory a boundedness constraint on the computational capacity, and one of the things that observers sampling is proposed to do is to increase the structured information every time it samples. That means finding pockets of what Stephen calls computational reducibility. So shortcuts, equivalences, many paths of computation that equal the same answer that you can shrink into your internal model and that then leads that exploit those equivalences so that more of your computational power is free to explore new choices. Michael Timothy Bennett just published a really interesting paper around why life emerges, and again, it's using sort of a computational argument, and would recommend it to anyone interested in sort of how the amount of states you have access to in your sort of computational buffer, as he calls it, determine or help determine whether you will survive or not. And so here I want to really talk about symmetry breaking as the mechanism of that. So broken symmetries mean more distinguishable states, and finding symmetry means finding pockets of reducibility where you can say the computation has got easier. I can always assume that this is the answer. I think here what we're saying is the symmetry breaking expands the observable Ruliad, mostly because perfect symmetry gives one single equivalence class and there's nothing that you can distinguish. When you break it, you get distinguishable states by the coset of it. And you can see this in sort of how the early universe built. The sequence of symmetry breakings from sort of SU5 down to SU3, SU2, and SU1, then down to the electroweak force and down to chirality. Each single breaking increases the number of patterns an observer can detect by orders of magnitude. So here, each breaking from the observer's perspective, which is what observer theory is about, is an information explosion. Like, R0 grows dramatically. And when you look at this from sort of the physics side, when you look at something like Noether's theorem, you can see that every continuous symmetry an observer detects is a compression opportunity. Translation invariance in Noether's theorem means one model covers every single location. Conserved quantities are like free compression of a fundamental computational object. And the observer's job here is to refine those symmetries because they reduce computational costs, and then to exploit those symmetry breakings, they expand the overall space. So there's this dynamic between exploit and explore that lives in basically every single observer that's implementing this 8-stage loop. I think one of the things that comes out of observer theory is sort of slightly different, I'd suppose, philosophy of science style predictions. And so really the main one I want to point your attention to is many worlds, because many worlds and the Ruliad share, if not, share the base of the idea together. And I think the core thing about many worlds is that many worlds is sort of, and all branches are equally real, and there is no preferred selection, there's no collapse. And I think observer theory is making a different point. It's saying that the observer's boundedness predominantly means that they're selecting branches in a computationally efficient way. So the branch rates track sort of structured information, and it's gradient-like, and again, it's the overlap, and it's bringing FEP into thoughts around how do many worlds make the one world we experience. And I think it's something like computational efficiency in that selection is a part of that answer. And I think the other one to talk about here is probably materialism, where the sort of theme on complex observation or consciousness arrives when there's sufficiently complex computation. There's no special role. And I think here this is where the sort of domain map earns its salt. And here the observer theory position is that consciousness requires information integration or structured information to be integrated across all the accessible domains. And so not all computation and observation will qualify for the label of conscious. And I think that's, for me, something when you talk about things like panpsychism, I think this is one of the issues that people have with it, is that when you talk about an electron or a particle being conscious, it imports a lot of history in that word. And I think it's much cleaner to say, well, this is doing a loop, but it's not like us. And I think that scale and that graduation is a more useful way of thinking about different classes of observers than, panpsychism's everything is conscious with no hierarchy or no way of determining how that hierarchy functions. And I think the rule constraints within the Ruliad that you import naturally from the structure of the object give you the ability to use those to determine those thresholds. And so that, I think, is quite a useful feature of the Ruliad's formalism when applied to ideas around observers and around things like active inference. So I'm going to just talk quickly about some of the implications for biology. Apologies if some of these slides were covered at the Platonic Symposium, but I think the main thing to talk about here is evolution as informational. And I think here we're saying that evolution by natural selection is very powerful, but because of no free lunch, it tells us it can't outperform a random search across all possible problems. And so the implication here is that the Ruliad more generally, and the observable Ruliad, is a highly structured landscape with lots of gradients. And that means that evolution functions well. And the explanation that comes out of observer theory is that physics, chemistry, and boundary conditions embed information that evolution tends to exploit. So convergent evolution is where you see this most clearly. It's bats and dolphins independently discovering echolocation. It's the evolution of eyes and 40 separate genuses. This gives the intuition that there are strong attractors in this computational possibility space that are computationally efficient at getting the observer to take in the most information for the least computational cost, i.e. that gradient is baked in and there are many gradients nested within it. And here we're saying that this isn't coincidence, it's that it's imposed by the structure and by the nature of a terminal object in that structure. The terminal object acts as sort of the ultimate gravity well, or the ultimate sink. And so everything, because the observer is never at that point, the observer is always effectively staring downhill. And then they're always traveling these gradients, and the job of the observer is to choose between faster and slower gradients. I think here we get some implications that fall out of this sort of idea. And the suggestion from observer theory and a computational model of observation is that survival and reproduction are instrumental. They're required so that observers persist long enough to continue finding structured information or integrating information. The deeper optimization, I think observer theory suggests, is that the thing you're selecting for is computationally efficient information gain. And in sort of a longer companion paper to this, I formalized this as sort of an informational return on computational investment. So for how many hops you take, how many states you update to get to more structured information, whatever your goal state is, that ratio determines for an observer how good or bad they're doing at it. And you can look at it now and see if you can recover sort of survival and reproduction, and you can look at it through sort of an animal that's doing predator avoidance. So here, that informational return on computational investment is massive. For technology, for people like us, it's the cost of it is amortized across millions upon millions of users. And so again, you get to some huge returns on the information gain for different objects, which lets you weigh what is a better or worse decision. So it's a slightly different framing for decision theory based on the actual structure of the landscape than you would get from, say, VN decision theory, which I think is quite useful and again aligns with active inference, which is really doing that sort of phase space gradient discovery in a manner that is just a slightly smaller universe than the Ruliad, right? This is really focused on brains and really focused on neuroscience. And here I think that active inference has discovered something sort of universal about that, especially the math of it, which lets it be applied more generally to how evolution works for a longer time frame. Again, if you can state it in computational language, because then you can comport it with the other work that's going on empirically in the space. And again, this probabilistic measure is hard to map to, is harder to map than a discrete measure. So I just want to quickly talk about the scales here when we think about observers. And so really the basic the basic premise at the beginning of the paper was that this is a universal observer model, that you can apply this boundedness, persistence, and relevance constraint to any class of observer as long as it satisfies the sort of minimal observer model function. And so here we look at sort of cosmic time, and we look at the types of the classes and sort of the affordances or the observational capacity, how much of that state space they have access to. And what you find is you have sort of a sigmoid style accretion. Apologies for this badly drawn chart. But once you get the CMB released and you get sort of your first minimal stable observers as atoms, when we get to molecules, we get an enormous explosion in combinatorics for how they can be put together. When you get to life, you get movement, you get self-replication, you get heritability, so that information you gain persists between generations. And then you go up to mind, and you can suddenly start acting in the world and changing it. So humans, compared to most animals, change their environment and impact their environment much more, where probably something like monkeys are in the sort of the middle ground. When we get to culture, this is determined by the ability to transmit that information between minds and across generations. So it's all about time and growth of that boundedness, because you have these are all builds of networks. So particles form atoms, form molecules, form life, form mind, form cultures. They're all nested like a Matryoshka Russian doll. And so that Russian doll, that affordance that you get from that stable whole, gives you access to more computational options. It's like the whole has a different board game that it can play compared to the parts. So for a mind can compose many problems and solve many problems. Cultures can solve more problems that individual minds or small groups of minds can't solve. And these are things like, politics, economics. In economics would be things like the invisible hand. That's a cultural object. That is not something that an individual mind or a small group of minds can make happen. And so really the scales are all about how much of the possibility space can an observer sample, integrate information about, and ultimately have causal influence over. And so on the right hand side, I've just looked at what those observation mechanics are for each of those to sort of to sort of kick the tires on whether these sort of classes are observers. And you can, if you look at sort of molecules, conformal scanning, reactivity, bonding networks. For basic life, you have sort of chemotaxis and gradient following. You have gap junctions for multicellular life, and for minds, you have specialized operators and network topology, where you get this clustering and path length that lets us start to say these things looking back down. And then plasticity, so you get the ability to alter that structure as you go. And so because of that, your ability to change the state space you can access sort of hits its limit once you reach a mind, because once you have plasticity and once you have the ability to change the network topology by reinforcing it, you can access with the same mind different sort of observable state spaces based on your causal history and based on what you currently do, so you can change it more actively. And that ability to have change and have agency is really what separates sort of mind from normal life in this class. The more your agency as an object goes up with this scale. Lastly, I just want to look at sort of coupling technologies, because I think it's very easy to bring this home with an example from how observers like us work. And so this page just shows that same chart applied to human sort of core technological changes that have enabled more humans to group and couple and share information. And I've tried to break this into sort of what I consider to be the biggest. And I think the two things you'll notice is that, one, the time periods get shorter and shorter, which is what you would expect in something that's sort of exponentially, it has any exponential relationship within it. But secondly, you see that the size of the groups change materially between phases. So from language, we get to Dunbar's number. From writing, we get, basically small cities and civilizations and empire. From the printing press, we get global knowledge and no longer local knowledge, and the coupling range becomes global. And then at the internet, we just have the cost go down, and the cost of delivering that information falls materially, and the range increases to anyone with an internet connection. We get an acceleration in the amount of effectively effective or structured information we're producing, even if some of that is not useful. And today we're going through this new phase transition. So what is AI doing? AI is materially accelerating that. So there have been stats around the composition of the internet in terms of content. And I think the estimate is something like 90% plus of the internet that you access will be AI generated before 2030. And so you get more and more information from more and more of these technologies, which lead to more and more humans being able to coordinate on bigger and bigger tasks. And this applies also to non-humans, except much, much slower, because they don't invent technologies like this that enable groups to grow. So just moving on to implications. So I want to talk about Telos. So here we've talked about sort of three general threads converging in observer theory, which is how does the state space work in physics? And we're talking about symmetry breaking fields and Planck limits defining that structured bounded universe. We're talking about evolution building increasingly powerful observers riding these gradients from less dense information to sort of the terminal object point of the most information. Here, one point to note, when you have a computational object like the Ruliad, what does the terminal object imply? It implies every computation is done. So it has the most information if the output of a computation is information at the most basic level, and therefore everything is effectively weighed against it. I think here when we look at observers, we're looking at complexity and those phase transitions, tracking how much and how deeply those observers can probe our universe or our reality. And I think the convergence suggests a core conjecture of the paper, which is all observers, if you're classifiable by this rubric, share the same fundamental goal: maximize integrated information or structured information subject to boundedness and persistence. And I'm not trying to make sort of a metaphysical claim about purpose here. I think it's more of a mathematical or biological claim in that systems that don't maintain positive information or lose their fight against entropy, they lose their boundaries. So they lose their Markovian blanket and they sort of dissolve into the ether of the Ruliad. And systems that maintain it persist and spawn more observers. And this is really natural selection stated information theoretically. This just talks about how we connect this back to the Ruliad, really, and it's looking at computational complexity. So the amount of steps you take, how many hypergraph updates do you compute to get a piece of information? And I'll run through this very fast, but O1 is directly accessible from your current state. So from hypergraph state 1 to 2, you can get the answer. ON is n hypergraph updates away. This matters because the hypergraph is posited to update at below Planck time speed. So lots of hypergraph updates could happen between one observable state change for you. ON squared means that you need to explore a 2D region of that hypergraph space. It's like a random walk. And O2N is a full multi-way exploration. So you're exploring the sort of multi-computational branches to find an answer. And O infinity is sort of the unreachable terminal object for bounded observers. And here, complexity measures the length and the structure of those morphism chains. So from the choice chains that you make from state 1 to state 2 to state n to get to your desired or your goal state. And this is to enable you to do discrete measures back on it to say, is this path more efficient or less efficient? So you have to set the goal state to do that. Here we have a general global goal state of sort of approaching or asymptotically approaching a terminal object, but you can compose that earlier in the chain and go to, this is the goal state now, this is the goal state in a year, and those can all interact in this sort of structured model. And I think the core question that comes out of this is, given limited computational resources, which path should observers invest in? And here it's working back to that sort of informational ratio. It's which strategies minimize cost per bit of useful information gained or structured information gained. So I want to talk a bit about information gradients in the Ruliad, and this is sort of a formalization of that sort of that cascade from sort of human from that terminal object, and looking at those domains and how informationally dense they are. So by informationally dense, what do I mean? I mean these objects in domain M will have more causal influence, more top-down causal influence, more formal causal influence, more macro causal influence, depending on the papers you read, than objects in domain P. And so that has more information density. You can imagine something like the form of the circle, if you want to be Platonic, having influence on every possible thing that's downstream of it, because every in sort of the P domain, because every fundamental particle is ultimately that's stable is ultimately a sphere, right? So these are sort of an intuitive way of getting that idea into your head. And I think here what we're saying is that different objects, even though they are embedded in this multi-domained Ruliad, because of their computational power, have access to different layers of it. So you can see something like this is again talking to that sort of point about making sort of claims in panpsychism or claims in consciousness studies more graded. So an atom is clearly interacting in the physical universe, but you would say that it's probably not got the computational power to access more complex informational objects in the sort of higher rule or the less rule constrained domains. Animals do more, humans do the most. AI may let us do more than that. Again, this is just taking you through that hierarchy in a way that hopefully makes it a bit clearer. But here we're breaking down constraints and embodiment versus integration abstraction going up. So at the bottom we have sort of the physical universe. This is O1 access, it's particles and fields. We have inferable patterns, these are preferences and goals. And we've tried to, in the first instance, say, well, how do we access those? What's the complexity of accessing those for an observer? And this sort of this O1 scaling up to O infinity at the top is saying that things like intuitable archetypes or computable structures like very big theories, they take a lot more computation to fully integrate into your world model than walking around or than an emotion that's hitting you when you respond to something. And so these different costs start to matter when you apply ideas in observer theory to things like metaethics, which I think is a natural extension, or to decision theory. So I think the key points are the higher domains contain and constrain the lower ones, and an observer in the P domain is effectively moving structured information upwards from raw data to value-laden meaning to abstract understanding. And you see these types of structures exist in several sort of wisdom traditions all across the world, in every religion and in philosophy. So hierarchy, and the sort of old idea is sort of something like an axis mundi in theology, is that they function as limit setting devices here. So they basically a projection of what they think the maximum accessible possibility space is. So the ideas of deities, or the ideas of gods, and the ideas of religions, or the ideas of Platonic forms, or a Spinozan nature. This is like the role of thinkers building the limit of the accessible state space. So saying, I think we can access this far. I think this is the limit for us. The limit of our observable Ruliad is some infinite deity, or something smaller, some Platonic form that's living there that we can access. And so you get this in different languages and these hierarchies, but they all have a similar structure with different demarcations between them. And here, what we're doing is applying those structures to a computational model. And generally, the point on the hierarchy is dependent on the researcher. So if you're looking at, say, a bat, you would not have this you may not look at this hierarchy, or you may break this hierarchy into different subdomains within the domain, and that's all possible again because you have a joined up map, you don't have a disjoint map. So I want to talk about sort of this structured information or information integration as universal telos just a bit more, and I think just trying to give people sort of more intuitive understanding. And the intuition here is that the observers that integrate more information predict better, survive longer, and spawn more observers. And then we can see this sort of in history, in biology, that organisms sense, integrate, respond better, outcompete. In culture, that societies that compress and share knowledge tend to thrive and live longer. And in spirituality, we see that traditions that guide attention towards bigger structures really than deeper structures, it's more the size of their ultimate object, they tend to persist. So all of the major sort of philosophical religions that persist today all have within their sort of belief system some ultimate object, some transcendent object, and the other ones have been outcompeted. I think here the important point is to now say, well, what does the world say about this sort of telos, or this sort of pull, and instead of a push? And I think we get from biology that nervous systems and memory systems all increase the amount of potential information we can access per unit energy. And we see that culture tends to externalize, compress, and share this information at a lower cost amongst a network of observers. And we're seeing that now come up in minimal experiments. So in some of Michael Levin's work, you see regenerative morphogenesis and non-neural cognition. You see perturbed algorithms solve outside of their algorithmic construct. So the bubble sort experiment is really interesting. And I think here the perspective that we have is really that you die out to entropy if you don't do that. And then as you become more complex, as you become a bigger object, or you get access to more of these layers, you have more causal influence in the entire observable Ruliad. Just the amount of choices you can make and the downstream cascading impacts of those choices have more impact in the entire system, or the entire sort of observable Ruliad, or the field of observation you're part of now. And then we talk about efficient search. So observers at every scale really evolve optimal strategies for exploring this computational possibility space given those constraints. And as strategies get more complex and sophisticated, they have more dynamic balance between exploration and exploitation. And as groups of observers come together, people split off and specialize, because exploration and exploitation are two they're orthogonal, and so you often find when you get to groups of observers that certain observers become very good at one and very bad at the other, and that's because that culture, that group of observers, is distinct and persistent in time, and therefore can allow that specialization to grow effectively to increase or decrease its boundedness, or increase its computational power, and solve this telos. So we walk through it and we see things like Brownian motion, where you have guaranteed coverage but no memory, and it's sort of the default that everything reverts to if everything else fails. Then you have gradient following, where you get local optimums, it's low memory, it's computationally untaxing, but you have plateau problems that you have to solve. So when there have been experiments on sort of evolutionary algorithms done by Stephen's team that show a gradient following sort of evolutionary algorithm, and it will bubble along for ages, reach a local peak, and then will stay flat for a long time, and it will randomly try rules like Brownian. It will revert to Brownian motion because it can't get out of that sort of local optima, and then it will randomly discover a new rule which exponentially jumps it up the fitness landscape, so it gets massive gains quickly. And then that process, that sort of sigmoid process, linear, exponential, linear, continues, and each time these evolutionary algorithms find an obstacle, they're effectively, in their current search, they effectively revert back to a simpler search to try and search more of the space faster. And so that moves to memory-based search, and that's where you start seeing animals, and you get planning, you get goal, and you get more goal direction, and you have an internal map that starts to update much more in much more complexity than with gradient following. And then we get to symbolic reasoning, and this allows big leaps, it allows huge compression, it allows cooperative search versus individual search, or or sort of a family of animals if they're traveling together based search. But you have some negatives that come up with that, where you have misalignment of the symbol with reality, i.e. the world model and the internal model don't match. Overfitting, where you take data and you basically make assumptions that skew the weighting, the probability weighting in your internal model, because You don't have full state space enumerability. You can't see all the options you don't know about. The sort of political the political meme of it is the sort of unknown speech that you get from Donald Rumsfeld as like the idea of that. And then you have a limit item, which is sort of quantum search, which is sort of a Grover-like limit in our universe. And then at the end, you get what religions talk about, which is direct knowing and mystical insight. And it's basically, I've got the download. And so these are all the types of search that you see of this map that computationally could be happening by the classes of observers we mentioned thus far. I think this just talks about, links it back to the efficiency versus the sort of energy cost, like how computationally efficient are these search strategies. So here we're looking at a measure of cost per bit, and at the moment one of the things I'm doing is updating the epiplex measure to be the measure space for this. And here we look at observers that can pay these upfront computational costs for building bigger world models. They tend to get long-term advantages in both integrating information or finding structured information, but also downstream of that in survival. Because their world model is more efficient, they have access to more possible states between sort of hypergraph updates or moment to moment than something that doesn't. And so here, the claim is that selection favors architectures implementing more efficient strategies, and that trajectory is basically universal, and that survival, again, is derivative. It's required so that you can continue to sample information. Before I jump into the ethics section, I just wanted to sort of talk about the thing that I'm currently working on, which I think links to this, but also links quite heavily to active inference. It's a work in progress, but I've been looking at the formal structure of decision theories, so VNM, causal decision theory, and Sals and Yudowski's functional decision theory. And I think the observer theory has helped pull out this hidden assumption. I've mentioned this word a few times so far, but state space enumerability. And that axiom seems to underpin every major decision theoretic framework except for active inference. But the agent, and it's really the agent, needs to be able to assign probabilities over the consequence space. And here what I'm going to be doing is using Rice's theorem from 1953. And I think we can, to mathematically prove that no bounded observer embedded in a computationally irreducible environment can satisfy this axiom. And this basically is saying that the consequence space for an observer like us is provably unmappable. And it suggests that it's not a computation problem, i.e. alignment is not a computation problem, it's not a smarter fix, it's about structural inaccessibility. And I think what's interesting for the sort of the theoretical neurobiology group is that active inference doesn't require that. And it navigates by local gradient. As you've probably seen from this paper, I'm very keen on them. And it minimizes free energy using only what's at the Markov blanket. So I think if this impossibility result holds up, it provides sort of independent mathematical justification from computability theory and not from physics as to why gradient-based approaches like active inference work when utility maximization fails. That paper's in review at the moment, so if anyone wants to have a look at it afterward, just drop me a message in the chat and I can send a draft. I think there's just one more piece I want to talk about, a work in progress. So in the papers and in the framework, information integration or structured information is sort of integrated by Phi, but it needs a tractable measure. So the paper by Finzi does that. It formalizes structural information extractable by a computationally bounded observer. It was being applied to LLMs to figure out how much they were learning in a training run. And here it separates that learnable structure, so this structured information or this pockets of computational reducibility that I've been discussing. And and it separates it from sort of genuine unpredictability, genuine computational irreducibility. And it's measured very simply as the area under a neural network's loss curve. So it's perfectly in line with sort of that gradient following. In the extension to the Ruliad, we're adding a second axis to this for observer relativity. So it's not just in the Finsey example what you can compute with the data, but it's which data you receive. And I think this gives us an operational measure for observer relative structured information. And I think it connects to the free energy principle, because free energy minimization is structure extraction. I think the agent, at least my take is that the agent is building a generative model that compresses those regularities in its sensory stream, and the quality of that compression is what epiplexity quantifies and measures. So I think those are two interesting things that lead on to this ethics section. And I think here, what we're saying, I think so far I've argued that the reality for observers is passable computationally, and the Ruliad is this limit object of computation. And because we're bounded samplers and this space is structured, the telos is imported by the structure of the space, and it's effectively moved down the gradient towards maximum information integration or maximum structured information as quick as they can. And here we've got ideas and cultural systems forming like a top-down or a macro causation superstructure that shapes the parts, the sub-observers in it, what they can actually do, what choices they can actually make, what they can actually be surprised by or not surprised by. And I think that the question comes then, well, if we do live in a structured universe full of these gradients, and there is some telic demand in some way, what does it say about ethics? And I think the claim that falls out of this structure of an observer is that morality must be discovered as a pattern of computation in this computational possibility space. But again, you could apply that to basically anything. I think ethical behavior here is mathematically optimal behavior, exploring the fastest gradients or the steepest gradients for the most observers. And so here we're reducing, you know, a huge amount of sort of meta ethics and ethical discussion and essay into a metric. And it might be a lossy metric, but you get a metric out of it. And I think it applies. And I think FEP is a formalism that's applying that in the choice moment to moment. And this is measuring it afterwards as a discrete measure. I think here, when we look at things like good and evil, or good and bad, or virtue and sin, they're about how much, they're really about a ratio of how much structured information your action produces versus the amount of sort of informational entropy for self-referential observers like us. And ethics here computationally comes out of asking which sequence of choices or morphisms between states are good or bad under this measure. So you still get globally an entropy increase, but locally observers create neg entropy, stability, boundaries, life more stable societies. And ethics here for observers like us is a study of which choices maximize that structured information per unit entropy, and which choices throw information away or accelerate that entropic gradient. So I think I wanted to work on choice. So this choice function looks at this scenario where sort of structured information maximization is a telos. Then ethics becomes the path selection question. And here we formalized it with a path cost function. So for a path through computational possibility space, the cost of that path, y, is the sum of the amount of computational steps it takes, i.e. whether it was O1, ON squared, etc. The distance between that choice and sort of the maximum, the point of maximum structured information in your model, the network effects on other observers, and the amount of entropy that choice generates between states. Now, the framework predicts that those paths that are good should have lower total cost, lower informational entropy, and faster conversion than bad paths. And it predicts independently evolved ethical systems should converge on the same computational optima, because the optimization landscape, the Ruliad, has one structure as a single object. And so we see convergence like this in what we observe. In history, you can look at major theological systems, major philosophical systems, but I'll give you a couple just to help. So we looked at the sort of eightfold path in Buddhism, and if you translate it to computational language, it seems to be talking about minimizing entropy. Christianity's commandments, love your God, love your neighbor, they translate to align with the terminal object in your model and maximize mutual information between observers. So when you put a computational lens on some of the heuristics that our systems have generated that seem to be very sticky over time, they seem to be doing computational work. They seem under this basic observer function of boundedness, persistence, and relevance, and a simple second order cybernetic loop. They seem to then do that. They seem to then do work on everything. It seems like lots and lots of systems and lots of our heuristics and lots of our sort of common knowledge is structured around these computational metrics and these computational limits that seem to be implicit in every observer. So here we looked at this, took this cost path function and then looked at seeing, well, what does that mean when you compare a choice, and this directly relevant to the decision theory work I'm doing. It's looking at cost and looking at the information gain and the entropy and the time. And you see that this is not sort of plucked out of thin air, that it falls out of the structure of the observable Ruliad. So if you have a structure like this where you don't have state space enumerability, you can only measure to some limit object that's a guess. You also have an observer loop where you're constantly weighing those choices against an internal model and expectation of those choices and a probability weighting of those choices. But you need to have some sort of ground to measure that against. And here we're saying that there's the structure of the space, that gradient structure implicit in sort of the information being computed in the Ruliad lets an observer climb those gradients or descend on those fastest gradients. And so here you can start to compare objects and you can start to compare what good and bad look like. And in fact, some of the people I'm working on sort of experiments with LLMs, they're doing this with LLMs and they're lighting up words and seeing what sort of what representations in latent space pop up for things that are deemed good and bad, and then comparing it to sets of human choices and seeing if you can do this measure, if you can import this measure from that work. I want to talk quickly about a time aspect here that is important for any sort of minimal ethical model of computational ethics. So I think the idea is called computational debt. I am unfortunately a person who has a finance background, and so I had to put the word debt in. But not all choices observers make are equal. Some choices create this computational debt where they appear optimal in the short term based on your current internal model, and that's your part of your computational boundedness and computational irreducibility of the whole space. But these choices, when made, require extensive additional computation in the future to integrate or structure coherently with the rest of the world model. And here it looks at the debt between the choice and the time as the cost of the actual choice that you've made versus the computational cost of the optimal choice, assuming you could know it. And then that is effectively the extra computation needed to maintain a suboptimal pattern, i.e. a pattern that is not computationally efficient. And in human sort of anthropomorphizing it, it's like a lie, it's addiction, could be even bad code if you're a developer. And then it's correcting it later, tell the truth and fixing the bug. And this is sort of trying to formalize in a decision theoretic way for an observer in a computational possibility space, the trade-off between the suboptimal decisions we make now versus the best decisions that we can make, because we often make decisions that seem irrational or seem suboptimal. But I think it's just a function of we think we're making the best decision we can make for us in that given moment, but our computational boundedness, where we're looking or where we're pointing in the observable area, what our overlap is with other observers constrains our ability to make rational choices over the whole space. We effectively are making a rational choice in a sort of very shrunken down version of that model, limited by your own causal history. So here, the position or the claim that observer theory is making is that ethics are part of reality's operating system. And because every persistent observer implements that same function and that loop, the ethics are discoveries of the optimal trajectories for that function. So here the ethics are really structural, like they are grounded, they are real as mathematics and physics. And again, the position of this paper is that all of those are discovered and not invented. So these are objects that exist in computational possibility space that we effectively access and map using our sort of computational capability. And so on the right hand side, I've sort of given something for intuition where we have sort of the hardware of this universe as this computational possibility space, the Ruliad. The kernel is something like physics, which is like the fields and the work, the universe we live in today. The operating system is something like computational ethics. And then the apps or the things that make those things come to life are cultures, institutions, and ultimately individuals. And so there's feedback from down and up that curve when observers interact with it. So just to conclude, I hope I've covered a lot and pretty fast, but we started with the Ruliad as as sort of the entangled limit of all possible computations, a limit object for computable structure. We had observers as bounded samplers running a universal loop, and undecidability that ultimate questions like will not be resolvable within the computational system. We showed how physics slots into this today, which is what what the Wolfram Physics project is doing, and they have got much more on sort of all of the underlying units and spacing in the Ruliad on the Wolfram Physics project website, which will detail how this can slot together. I think the things we're claiming a reframe of evolution as sort of an optimization or a maximization of structured information. We're looking at universal telos for all possible observers who are defined by this model as structuring as much information as they possibly can in the shortest possible time due to their boundedness and persistence. And then we formalize computational ethics through path selection criteria. And the decision theory paper is aiming to recover active inference as a sort of special case of this path selection, and it's being worked on at the moment. And then I just wanted to talk about what's new and what isn't, because it looks like, it's a pretty presentation with a lot of stuff in it, but I think that it's very clear to sort of set the boundaries where it's not new. Using computation as a lens on physics is done by lots and lots of different people. And I think it's not new to use information complexity and causal histories to talk about life and mind. In fact, that is what active inference does. And I think it's not new to recognize the ethical convergences across traditions, which is what metaethics does. But I think adding this observer overlay gives a single way to discuss that measurement from atoms to humans. It helps you determine how observers interact at all scales and not just at human scales and not just at animal, but all the way down. And I think you can start to form ideas. And I think this is part of the reason why I was invited to the Platonic Symposium, because you can build out models of memetics on this and how ideas and how those sort of informational objects ingress or are sampled by observers in the physical world. And then you can also start testing these sort of computational formulations of telos and ethics and see if they hold. Whereas I think with sort of bit style measures or structured information measures, which I think is really helpful when bringing like phenomenal ideas like active inference into decision theory, into physics, into the sciences. And so, yeah, thank you very much for the time. That's all I've got for you. So if there are any questions, please feel free.
Thank you so much, Sam, for the presentation. That's quite impressive, like lots of different topics and how they're connected. Really interesting. So yeah, now we move to the Q&A. If there are like questions or comments, please raise your hand. I'm sure there will be some. So I just have like a general. So does this? I was just like thinking, well, you were talking whether what would be like the prescriptive of the like how would you like operationalize all these? As in, it's clear that you have to have all these bounded rationality framework in mind when like that's what you've been saying all the time. Like you have to take into account the computational resources of an agent, and that's gonna tell you what kind of paths it can traverse through this Ruliad. Um, but I guess like you could have like two different ways to operationalize these, as in you can have some sort of optimal or approximately optimal strategy, and you say, okay, I'm gonna follow that strategy, and then I'm gonna put the constraints in it. Whereas you can do also like the other way around, which might not be equivalent, which is, okay, I know there are all these constraints, then I'm gonna try to find what's the optimal given the constraints, rather than the other way around,
Yeah,
if
I
that makes
think
sense.
yeah,
I
yeah.
don't know which one are you have in mind, or whether, yeah,
I,
something.
so I think the version I have in mind is looking at it from. I don't think you need the control. I don't know if you need the control of like a limit or a goal. I think you can just do it on the measure of state to state from the information from sort of the structured information generated between 2 points or between 2 points in time. So if structured information is rising, or the ratio of structured information to sort of entropy generated is rising, then that should be a good, and that should be able to direct you in that space and tell you which way they're going. I think you kind of run into like a Goodhart's law problem if you set a goal. Like, you get the overfit problem, and that's one of the like, this is sort of a core point of the. And just to give you clarity, right, this paper is being worked on right now, so it's subject to adjustments to whatever I say now. But I think
Uh-huh. Okay, yeah.
the general view I have is that if you're thinking about this, why am I thinking about this now? Well, we're working on perhaps the biggest decision theory thing that we will ever work on, which is we are currently shepherding into the world a bunch of very smart systems that seem to do stuff. And all the decision theory apparatus that we have, X active inference, seems to have a very limit. And these are discrete formulations, right? So like bounded rationalities, like they all have bake in this implicit assumption that they can set the state space, that they know and can make probabilities over the entire state space. And that's just, I think, false. And I think it's mathematically false. And therefore, if you're going to bake in any sort of goal in alignment, then you need to bake in the goal as like a direction of travel, which is why that structured information to entropy is like a gradient measure. It's just a gradient measure. And so that's how I'm trying to make a discrete gradient measure for something probabilistic in the current formulation of FEP and active inference, because it's right. You can't stick it in a computer right now. And that's kind of where this work is going. It's trying to take these brilliant ideas of active inference and say, well, we're working in a computable world, and Bayesian probability over a big gigantic Markov blanket is very hard to do. Can we do a tiny bit? Can we figure out a clever way to do better? And I think that the neat thing about the Ruliad is it's discrete. It is discrete, and so you get a load of, and you can use category theory, and you can use all of these tools that make it algebraic, which help you to do that in a way that makes that question answerable. Does that hopefully that gave you sort of a good answer as to the direction. Just tell me if it didn't.
Yeah, yeah. It was just because I had in mind when you mentioned that the epiplexity paper,
Mm.
which is a really, really good one. Um, it's nice to see how, for certain cases, how being computationally bounded is gonna interfere with the notions we have about information. Some cases where completely deterministic setup where no information should be transmitted in the system because it's just deterministic. So from the initial conditions, you can just like roll out and have all the next states. But when you are computationally bounded, you have to coarse grain or like do some sort of operation on the next state so that you simplify them in some way. And that simplification or coarse graining is just it's gonna generate uncertainty towards the future, right? And it's gonna generate um therefore like some information in that sense. So I was like just thinking how all these notions of perplexity or computationally bounded information theoretic perspective fits into the when you were mentioning like active inference or or
Yeah.
FEP in general. I don't know if you had like something in mind in which those two things are related, more in abstract terms.
Yeah. So, okay, so working back to the original extension paper, you sort of the observers are finding equivalences when they make a sampling in an object that they're basically trying to stabilize or trying to reduce the surprise in, and they reduce the entropy, and then there's some minimal entropic state of that object, and that delta is the delta that those sampling is shrinking. And so when
Hmm.
you look at epiplexity, well, epiplexity, I think, is the measure of how that sample is shrinking. And so because the sort of entropy, the differential between the entropy you've taken down and the minimum is effectively like a surprise through time until there's no more surprise from sort of a sampling that you're making that as a sort of active inference agent in a Markov blanket, you can use the epiplexity and the discrete formulation of that and sub out and say surprise is equivalent or roughly equivalent. It might be weakly equivalent. It might not be exactly the same. I need to finish the paper, but
Okay. Okay.
that's sort of the instinct of that research line, right? That can I can I effectively take focused a surprise focused framework that seems to be more general than just a human brain, right? This is like the work Carl's doing with Chris Fields, right? Like this is it's more general than the human brain, but the format of it doesn't fit with how this is done. This is done in sort of LLM simulations currently. It's computationally expensive, so there must be a simpler way. And this epiplexity paper seems to decompose for a bounded agent, right? It's literally all about bounded observers. So, I could have paid them to make that paper for me. They've done me a huge favor because I like the sort of K complexity as a measure for that space. You lose stuff from it. It's really coarse and it doesn't always come out and it's hard to compute. And so I think this is quite a neat way of solving that problem and bridging that gap where you can, instead of using that sort of adjusted K complexity measure, you can use some adaptation of this to then run simulations for agents making decisions under an active inference framework with LLMs that actually get you outputs that are not probabilistic, that go, no, this reduced surprise by X, and this is the minimum surprise this thing could have. So it lets you start to say things in a way, I think, that make it much more functional in the world we're going into versus operationalizing it for sort of the AI universe, where I think these sorts of experiments will have huge value, is the way I describe it.
Okay. Yes. Yes. Good. Thank you. Yeah, Alexander, have you hand raised?
Hey, thank you. I thought that was a really interesting talk. Something I just wanted to ask was, it seems to me as though there's potentially some overlap between the framework that you're working on and developing more broadly and integrated information theory.
Yeah.
And not just sort of specifically around information being integrated, right? But when you talk about there being kind of I believe he said something about there being like maximal like locuses of cause effect power and stuff like that.
Yeah.
And that struck me as very similar to some work that Tononi has done, like within IIT and also within some sort of adjacent papers. So a bit of a big question, but I was wondering if you kind of like see, because you also think this has quite a strong bridge with FEP and active inference, whether you kind of feel like there's any scope for like formalizing a proposed relationship between them, like in a bit more depth and stuff through this tool.
Yeah, so you've nailed it on the head. Like, what is this thing, right? It is a tool, right? Because it's meant to apply to all observers from an atom to a human, right? It strips out some of the things that make IIT and make FEP or active inference FEP, because you can't have all of those things. Some of those things, for example, in the original active inference papers, just apply to humans. Some of the things in IIT don't apply even to animals within IIT. Like, they have different classifications at different levels. And here, integrated information, when I wrote the original paper over the, like, it was, you know, last May it came out, and a year before that I was working on it. Integrated information was, it felt like the natural way to frame the output of a computation that an observer finds useful, and maybe because it really is a composition of domain samplings into a single object. Now, the irony of the Finzi paper is that structured information feels like a much more natural way of saying that, because integrated information, you import a bunch of criticisms about the words integrated information when you use it, which is like, you can't compute this ever. This thing, if you perturb it once, then the universe has run 100 times before you've got an answer. The math is, it's a great theory. Math, this is the classic sort of IIT thing. It's pseudoscience that can't be. And here, when that paper came out, I was like, oh no, that's what that is. That's not, it's not. So the new paper, the perplexity adaptation of that metric to this model will replace integrated information with structured information. But do I think that that's what IIT is actually measuring? Yes, I think that's what they're actually measuring. Like, I think this is the best, for a bounded observer, this is the best measure paper I've seen in 2 years, right? Like, it's much more useful than sort of the PRH measures or some of the kernel measures that you get from other sort of AI papers, because it's more adaptable to other things. Like, those things are like, oh, if you're not a neural network, then I'm not going to get an answer. Whereas that structured information, you could easily adapt that to a sampling from a camera. You can, you know, that's why I think it's much more useful. And do I think that IIT and sort of FEP kind of link up? I mean, this is, you know, shooting from the cuff a bit, because but do I think FEP is the more complete theory, and it's the more functional theory, and it's the more useful theory? So really, if IIT is just keeping that word, that's kind of like, I just think it's going to get replaced by better theories that are more tractable. I think the idea of it will be kept, the intuition that there is some integration across zones, and you've seen it in the PID. They did the paper in September on PID decomposition, where they split the brain into, like, it was like 4 levels that coherently came together, which made it a bit more computable. And so I think that's kind of the domains in action, showing that that's giving you more compression, so you can actually compute this thing. And then you've got FEP as the measure of whether what you computed is good, bad for the organism or the thing that's doing that computing. So that is sort of the shoot from the cuff of how I think it works together. But hopefully that was that. I haven't thought about that in any depth, in any major depth. So
interesting. Thank you.
Thank you, Alexander, for the question. Let's see if there are any other questions on the chat. Yeah, so if not, I guess we can move on to you, Carl.
I was just finishing my cigarette. Is it my turn?
Good man. It's nice and as unhealthy as I am then. Perfect.
Very good. Right, so it's my turn now. Excellent. Yeah, yeah, that was wonderful. I mean, far too much material. So you should be.
I've not done many. I've not done. This is like my 3rd one, so you know, I'm not trained. I'm not trained, but everyone else seems to have much less in their presentations. So.
Yes, well, as time goes on, you will get into the swing of carving up what you want to talk about and what you don't, and it's an awful process, but it has to be done, especially when you've got word limitations on peer-reviewed publications. That's one of the worst things, is throwing away all your favorite material. But practically that means I can't speak to everything that you've spoken about. I'm going to speak quickly, because I realize now you've been on stage for an hour and a half, and I know that this is being recorded. I hope it is being recorded. I presume it is being recorded. Yes, it is. So that, you know, if I say anything that's going to be of use in nuancing your current paper and subsequent papers, then you can go back to it. Otherwise, you can ignore it. what I normally do at this stage is just try and pick out some of the enduring themes. And what I've done is, whilst I was listening to you talk, just identify a few papers, which I suspect you've probably read, but some of them you might not have done. That's nice.
Well, I think it's coming from Sam. Can you hear us, Sam? Oh, I can. I'll just mute you for now, Sam, because there's like some sound coming out from your laptop. Yeah, thank you. Now you're muted too, Carl.
Oh, I see. Sorry, I was just talking to you. Right. So, yes, I was trying to say, can you mute Sam? And now Sam's disappeared completely.
Yeah, just Sam,
Oh,
if you
hang
can
on.
hear us.
He's
Okay, you
coming
can hear
back.
us.
There
Okay,
he
nice.
is. Very good.
Perfect.
Everything's back to normal-ish. Good. And Centra is unmuted as well. Right. Yeah. So I would say I've got about several papers that I just want to flash up so you can see the reference and very briefly explain why I think you might be interested in reading them. If not, the agenda here is just to feed back purely from the perspective of the free energy principle and active inference. Largely, in fact, universally, just to endorse all the points that you've made. I can't endorse all of them because you've made too many points, but a number of them sort of rang true. And in I thought it'd be useful just to sort of clarify how the free energy principle would say yes, that sounds absolutely sensible. And then qualify it by saying, well, yes, it sounds sensible, and it's certainly one of the tenets of an emergent property of the free energy principle, but you'd require some heavy lifting to put it in terms of Wolfram physics. You require some heavy lifting to articulate it in terms of Chris Field's quantum information theoretic treatment, and other sort of formalisms that have a broader scope, things like category theory and the like. So the free energy principle tries to keep away from category theory and quantum information theory, and the kind of sort of universal computation that one finds with the Wolfram formulation, largely because it wants to be true to its physics heritage. And to be able to talk to Hermann Helmholtz, to be able to talk about sort of the way that people have been talking about the physics of things over the past century. And it also keeps the math simple, which means that I'm not going to be too challenged and don't have to rush off to Wikipedia all the time. So people have tried to drag us into category theory and the like, and it hasn't worked. And indeed, tried to articulate these things in terms of pure as opposed to applied mathematics. And that's above my pay grade. So I'm going to try and dumb down and say I liked what you said, and this is how a physicist would express it. And we're not talking about Stephen Wolfram. We're talking about Hermann Helmholtz, or a current student of effectively classical physics. And on that view, I think just starting at the beginning where you did, the Ruliad would just be simply be a random dynamical system that possesses a random dynamical attractor or a global attractor in the sense of random dynamical systems. And when cast in terms of continuous state spaces, that would just be the non-equilibrium steady state solution to a a random differential equation, such as a Langevin equation. And that's where all physics, to my mind, starts. So you can spin off quantum mechanics via by the Schrodinger wave equation. You can sort of get into stochastic thermodynamics and thereby statistical mechanics from that by sort of making ensemble assumptions, and you can even get to Newtonian mechanics and relativity by ignoring the random fluctuations, all of these being special cases. And the FEP is no different. It just says that if you can identify what you mean by an observer, and I'll use that because I like that. I think, I've started using that more and more nowadays. Then you get a Bayesian mechanics, and the Bayesian mechanics just does what you says. It finds those paths of least action where the action is the path integral or the time integral of an energy functional that comprises the constraints and the information gradients or the mutual information that just is, at one level, that the structured information. The twist here, I think, from your point of view, just listening as you talk about the importance of probability theory, is that the offering of the free energy principle in relation to the separation of the observer from the observed via a Markov boundary or a set of states that constitute that boundary, your inputs and outputs, effectively, is written in terms of cause-effect structures of a simple physicist's sort. So I'm talking about causality in a control theoretic, or as a physicist would talk about it. So this, where you are in state space causes the direction of travel. And implicitly, very much like your very first slide, in putting a lot of pressure on time. So the probabilistic aspects of random dynamical systems are just expressed in terms of the fact that there's a lawful mapping between where you are in some state space and your direction of travel, and that could be a deterministic mapping, but there are certain, but via a separation of temporal scales into fast and slow, you assign the fast stuff a description of a probabilistic sort. So you now have notions of Wiener processes or random fluctuations, innovations, that now can only be described in terms of their second order statistics, simply because you have, by the time the observer has actually inferred the state of these fast things, they've dissipated, they've disappeared. So they can't. So you do get a probabilistic aspect to the Langevin equation, and implicitly stochastic thermodynamics, but it's not, it's emergent simply because of time. And as soon as there's time, there's fast and slow. But the causality is just, as I say, that mapping between the state of something and its dynamics or its flow or change with time, and that's the Markov blanket can be defined in terms of those causal influences. And then the trick, or the offering of the free energy principle, is to say, from that definition of causality that defines or separates the observed from the observed, you can then get a probabilistic expression a la Judea-Pearl. So that's the, I think probably an underappreciated move, that it's the deriving a probabilistic Markov blanket in terms of conditional independences from the actual underlying cause-effect structure. And the cause-effect structure is meant in exactly the same sense that you were talking about in terms of structured information. It is the thing that links where you are in some Ruliad, I guess, or some state space, to where you go next. Sorry, yes, whenever you turn your microphone on.
Yeah, I mute you, Sam, because there's this sound coming off again.
if you can't hear yourself, Sam, you're basically going bum 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 bum
Yeah,
bum
basically.
bum 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 bum, as if there's some sort of you've incarcerated a feedback loop that is just
Is
regurgitating.
that better?
Oh yes, that works.
Yeah,
Yeah.
now it's
Sorry,
perfect. Yeah.
sorry guys, apologies. Yeah, no, I just wanted to ask the question. So just for my understanding, when you say that there's sort of, I'm going to put words in your mouth, but sort of a deterministic space underlying it, which is kind of like slow, and then you've got fast. Is that fast and slow within the observer's internal model, or is it sort of extrinsic to it? Is it sort of constructed within the observer, and so they have sort of like a Kahneman type 1, type 2 type thinking, where the type 1 is always continually popping out new probabilities as the type 2 system computes, or is
Yeah.
that right?
Yes. So the observer is just a subset of these states and conforms to exactly the same cause effect structure that we talked about before, which is written down as a random dynamical system. When the observer is very, very small, and I'm speaking polemically here, but this is a story that I would tell if I was king. Then for very small things, the very fast stuff known in my world as a random fluctuation, and the world of stochastic thermodynamics as a random fluctuation, dominates. So you basically get lots. You can only describe very small things probabilistically, and that is quantum mechanics.
Yeah.
But as you get bigger, exactly in the way that you were talking about in terms of moving from atoms or small particles to atoms to molecules to cells to multicellular, right through to culture. As you get bigger and bigger and bigger in scale, both in space and time, the fast random fluctuations average away. So, you were talking about nested Markov blankets, and as you're projecting the internal stuff onto the Markov blanket, in virtue of that projection and in virtue of the coarse graining that you get, the random fluctuations become averaged away. And then what you're left with is the non-dissipative dynamics. So I'm appealing here to something, again, illustrating the benefits of being able to talk to Helmholtz. I'm illustrating or telling this story, which turns on the fundamental lemma theorem of vector calculus or variational calculus, also known as the Helmholtz-Hodge decomposition, which basically decomposes any dynamics, any flow, into a non-dissipative and a dissipative part. And the dissipative part flows down the information gradients. But there's another part that circulates on the isocontours of that Lagrangian or potential, the functional that provides your information that possesses a gradient. And for me, obviously, that's the variation free energy. And that circular aspect now emerges as you increase scale. So as you get bigger and bigger and move to sort of multicellular organisms and indeed to things like us, then you have an admixture of the dissipative and non-dissipative dynamics. So remember Prigoghine's dissipative structures? So structure is going to figure a lot in I think my feedback to you, because it figured a lot in your presentation in terms of structured information. So in dissipative structures, there is by definition a dissipative part to the dynamics, and that is the information gradient flow. But there's also a non-dissipative part, and that depends upon the random fluctuations. So in the absence of any random fluctuations, you will not be able to explore those gradients, and there will be no gradient flow. So you won't have a dissipative structure. But there's another part, which is a non-dissipative part, and that's variously referred to as the curl or the divergence free or the solenoidal or the conservative flow. And as you get bigger, that starts to dominate over the dissipative part, and it is that produces life cycles, oscillations, biorhythm, replication, reproduction. As you get bigger and bigger and bigger, then all the random fluctuations, the dissipative part just disappears. All the stuff that the second law likes, all the stuff
it's
that's
like the thermodynamic floor of any decision, right? This is part of the decision theory work, and this epilepsy work is about decomposing that thermodynamic flaw in a decision, because we're about to go into a world where effectively computers are going to be making large majority of purchasing decisions, where you can for the first time decompose those streams in a decision that's economic. So you can start to, I think this is one of the neat things about thinking in terms of sort of FEP or in active inference or in terms of networked models of how these things fit together, is we are literally importing that to our entire economy right now. Yet we're still talking about measures like GDP, measures that are going to have ghosts in them from this type of work. And here we, with that sort of decomposition, you can split out though that thermodynamic part from the dissipative part, which is the sort of the structured part going down. And therefore you can get to, I think that's what's going on right now, is we're going to get to a point where in the stochastic underlying thing, which is an LLM, measures like yours are going to need to be used to do alignment, period. Like it won't work on because of all of the things I talked about in my talk, but you need to adapt that. That's the step that really I'm trying to take, is to take this and go, can I make this computable within the architecture of some decision making framework? Because here that is exactly the problem, where we're not even looking at it at the moment. It's not even being looked at, even though it's being put into everybody's phone and computer constantly. So I think it's quite interesting.
I see. Well, if you want to tell that story, I think you could certainly underwrite it with a couple of examples. Just to complete the sort of the scale, moving through different scales. When you get very large, like the size of the moon and the heavenly bodies, then it's purely solenoidal. You have n-body deterministic problems, and then you get relativity and Newtonian mechanics. So that, you know, talking about classical mechanics, when I mentioned classical mechanics before, I didn't mean to imply it's just solenoidal. But to come to your point about large language models and what's special about observers like us, one thing which I didn't mention is that those observers that have planning and can do system 2 or sort of thinking slow, do actually have to be random dynamical systems with very, very low amplitude random fluctuations. They have to be very, very precise, like a von Neumann computer. And if you wanted an example of what you just said, although it might be quite tenuous, but it's there all the same, then you can, to a certain extent, at least heuristically, decompose state estimation and Bayesian filtering into a dissipative and non-dissipative part. And technically, the non-dissipative part is the prediction, and then the update is the dissipative correction information gradient part of it. And that means that what you just said, I think, is absolutely true of large language models. If you now look at a large language model as some highly nonlinear Bayesian filter, and in fact, interestingly, Chris Buckley's group have written a paper showing that attention heads play the role of a Kalman gain in a Kalman filter, which is the simplest kind of Bayesian filter you can get. So I certainly think you could sort of tell a really nice story about it's not all about probabilistic. There's always a non-probabilistic, non-dissipative part to any computation that you can read either as the prediction part. So I think of this in terms of, if I'm doing belief updating or state estimation given some content or data in the service, say, predicting the next token or the next word. If I have a prediction before I see the data, I can't, if you like, change the information energy because I've got no new information. So that will be the prediction part, the non-dissipative part of the dynamics that describe a large language model. Yeah. But as soon as I get the next bit of information, I've now got the opportunity to do my belief updating, moving on an information manifold, and then descending those information gradients. So I think it's a nice example, of that appreciation that computation is not all about it's not all about dissipative probabilistic dynamics. In big things and precise computations, that there's a lot of this sort of non-dissipative part going on. And I would argue that to be biological is to have to be basically a non-dissipative system immersed in a dissipative system. So the observer is usually, observers like you and me are non-dissipative largely. Yet we have to establish a mutual information or generalized synchrony with the observed. And that's measured by the mutual information that you were talking about. So when you talk about structured information, I heard the mutual information. I heard the mutual information between the observer and the observed. And of course, if the observed...
I think it's exactly right. Like, I think here there's a, I was talking about this with Michael after, and Chris, it's like there's a lexicon problem across, because a lot of people, I think, are in the same wheelhouse of where the idea lives and what the thing, like mutual information and structured information in that context are effectively talking about almost, I imagine, almost the same thing. And there are a lot, and this is what I picked up. I don't know if you picked this up from the Platonic Symposium, but one of the things I picked up was that I'd say half the people were talking about exactly the same stuff with all of their slightly different languages. Yes. And I felt like a cartography or like a lexicography of like this space should be sort of pulled together. I think it would be very valuable, because a lot of people are talking about different words for, Michael says Platonic space, which is not actually Plato's Platonic space, and someone else says that, I say, computational possibility space, and someone else says state space, but I feel they're probably all reasonably similar things. And so given this sort of direction where you have a lot of the tooling sits in FEP, I think, already. And I think a lot of that tooling, like, there needs to be some lexicography that pulls it all together, because I think a lot of people are going in the same rough research direction of what they're thinking about. But everyone, and even like I had this discussion with Stephen, everyone has their sort of pet words that they like. And I think it just needs to be like one set of words, and everyone updates their historic papers for it, because at the moment we're sort of making like a bush of a tree instead of like a branch, or and I think that that's probably something that needs to be done, because it seems like there's a lot of overlap with lots of these things, all from slightly different angles or different backgrounds.
Yeah, well, I'm glad you said that, because what I was saying, I'm trying to give you things that allow you to join the dots or articulate it sort of from different perspectives. I was intimating exactly what you say, that I think you're in a great position to write down that to join the dots and have a lexicography that sort of identifies those cross-cutting themes, and from my perspective that they are exactly all the same. But I have to always do a sort of mental thesaurus and translation in my head and work out who I'm talking to. So when I'm talking to you, I'm talking about information gradients. Of course, if I was talking to somebody else, it'd be free energy gradients. So I'm talking to Herman Haken, it would be free energy gradients. It just depends who you're talking to. But having said that, I think this notion of structure. Oh, you're doing it again. I don't know if you can hear me, but your microphone has gone into one of those little loops again. That's okay. Very good. Yeah. So perhaps, in the sake of time, I should just turn to. I've never used the word lexicography before, so I'll have to practice it. But that's exactly what we need, and it's exactly why I wanted to, run through these papers, just to sort of allow you to sort of pull together the different the different perspectives and rhetoric associated with, to my mind, exactly the same ideas, with the exception, of course, that the Ruliad and much of quantum information theory does commit to a certain kind of discretization. You don't need that in the free energy principle, but at some point it is useful, I think, to think about things in terms of this discrete objects, and that's important, as you pointed out, because once you do, the gradients disappear in the fond sense of backpropagation and optimization. And that sort of move to a coarse-grained discrete kind of state space, or Ruliad, is really prominent in the active inference space when you work with discrete state space models. And I think that we're getting much closer then to a Ruliad-like kind of structure. But it gets even more prescient when you think about the structure learning problem itself. Now, you didn't mention structure learning, but I did interpret some of your observations as really addressing the deep problem of the very structure of the generative models that are entailed by an observer that allow it to maintain a high degree of mutual information with the observed.
Yeah, so I had to take, because of the time I took, there's a big section on like how you embed ideas in the paper and how these ideas work and how you basically create these equivalences that reinforce these loops. So the paper, the long form paper, which is sort of applying the mathematical apparatus of this extension to generally different topics, some of them I covered in this talk. That paper talks about structure and learning. And there's a proof I think in the original paper about the structure of learning if an observer has, in the appendix of the May paper, that talks about if you have a state space that's very minimal, like a toy model state space, well, what happens to the observer when it discovers all the rules, and does it cycle? Does it just meet your plateau? And you can prove that behavior happens with these types of constraints. And then the longer form applied paper really does talk about, well, what does learning look like? How do, one of the questions is, how do these abstract thought objects, the space of possible ideas that you can have is infinitely bigger than the space of possible things that you can bring into the world. And it's, how do you take something from that space of potential ideas that you can articulate as sort of loosely or as tightly as you want, and how do those things get embedded in physical reality? Well, you have this same iteration cycle, but for ideas, and ideas act mimetically. They're effectively evolutionary. They have their own evolutionary landscape and arena, which I thought, given Richard Dawkins sort of birthed this word, the fact that he didn't do, like, this is like, to me, the arena of evolution today is like this arena, this mimetic arena of structure, learn, and ideas have properties that let them spread, have utility, and we sort of have like a mixing board of a few tweaks a few things we can turn that let us tell us how that idea is going to embed in this space, which I think ties back to the surprise in FEP, because if you know the composition of an idea and its properties and how they embed, then you should be able to project surprise from that idea to an agent of a given type or a given computational power, or with a given model. And so I think like a lot of the people I do research with on memetics, and they're much more experienced. I tend to be like, oh, this is a formal observer model, but they run these sorts of experiments are happening all the time, constantly, by companies and by researchers on social media, where they're seeing how ideas embed and how they spread through these sort of network or tree style graphs of it. And you can start with observer theory and this idea of how this discrete structure, because of the discreteness, you can take points where it embeds and you can say, oh, this is step one, this is the idea coming in, this is the idea being tested, and then you can measure at each point with this sort of structured information measure that lets you say things about that generation over time. And so certain type classes of ideas may generate more structured information faster. Some may take, might be a flat line for ages, and then they generate enormous amounts of structure. You can think of when you published FEP, right? That probably took you a very, very long time, and then suddenly you got a drop of all this structure, and that was effectively, and I think that to me is one of the interesting things you can do with observer theory. You can actually start to bring in memetics and like the language of evolution of ideas, which into a language that comports or that is conciliant with the language of biological evolution in the same maths. And that to me is like, even if they're saying very different things and one is much more coarse than the other because of the nature of the different topics, the fact that they can be stated in the same language is valuable in and of itself, because you can always tighten the language and improve the math and improve the formalism. But if the bucket is the same bucket, I think it's useful.
Yeah, no, I agree entirely. Let me give you an example of that, just for your entertainment. I might have to request control of the screen. There we go.
Yeah, I think now you should be able.
Good. So where's So yeah, I remember you were talking about that what could be read as sort of cultural niche construction under a from my perspective Bayesian model selection or natural selection read as a marginal likelihood maximization or surprise minimization process. This is a purely narrative account by colleagues. He's a sort of key paleoanthropologist. I noticed one of your slide was sort of querying Dawkins' quest for evidence for this, and you're also talking about the size of the group being a key determinant of exploring new memes and doing things in a novel or creative or inventive way. And this is a very dense but beautifully written paper for anthropologists, and particularly paleoanthropologists, about the emergence of hand axes as a key tool, and just looking at the available evidence for whether this was, as commonly understood, something that emerged slowly or was actually an example of convergent evolution. And the answer is convergent evolution, but only in groups that were large enough to be able to become philosophers and to sit back and recognize that somebody had actually introduced a new tool, namely an axe. So if you wanted an example of in a completely different sphere of what you were talking about, then the snakes and ladders in paleoanthropology would be an entertaining one. I can't see you anymore, which is a shame. So tell me if you.
I can. Can you hear me? I'm here. I can see myself on the screen.
Oh, good. Right. Okay. I wonder why I can't see it. Never mind. Just a couple of things which I was smiling at. Sort of, your latter discussion about, is there any opportunity to bring IIT into the campus of the FEP and make it work as a sort of tractable measure of that structured information? The reason I was smiling is that IIT. Julia Tonelli used to be one of my best friends when I was in America, and I just remembered, and I thought this for a long time. So in 1995, this was a paper that Julia and I wrote together, applying embryonic IIT ideas to information in neuronal networks, as measured, I think, by PET and then subsequently fMRI. So in many respects, if you can bring IIT and FEP back together, that will be a rejoining of stuff that was actually conjoined right at its inception. The other thing that I sort of picked up on was your important observation that given you come from an economics background, that the application of probability distributions or probabilistic inference in event spaces that haven't even been defined. It reminded me of this notion of radical uncertainty by people like John Kay. And I'm not suggesting you read this because this is my response, but it was a response to a paper that referred to the notion of radical uncertainty in economics through the lens of conviction narrative theory. But my response was, you can actually solve the problem of radical uncertainty through structure learning in exactly the way that we were just discussing in terms of creating memes or being able to recognize completely new ways of doing that. And then what's this? Yeah, I just put this up just to reiterate and just make explicit. I'm not sure how much you know about the sort of the information theoretic underpinnings of active inference, but you can look at this. The path of greatest efficiency, the path that most quickly compresses information and installs structured information into a generative model. In my world, it just is the path of least action. So the free energy principle just is a variational principle of least action. When it comes to things that plan, when it comes to things like you and me that have a sort of multicellular, deeply structured, hierarchically structured set of dependencies and implicitly generative models, then that planning underwrites the choice of our actions with the notion that there is some intended outcome, and that intended outcome is very much in the spirit of your ethical treatment. Just is the expected evidence or the expected negative expected free energy consequence upon pursuing that particular path into the future, and you're trying to find that path. You said take a cross section or a slice through the Ruliad. I read that as basically finding the path of least action that keeps you in your attracting set on your terminal or your true.
This is exactly right. Yeah, like this is the whole, like, yes, it's really like you get some point in this object at the end of the line where everything has happened, right? You can imagine the Ruliad runs and every computation completes because we're infinitely powered. That has all of the data string. Imagine it was just text strings. It has every text string in it. And so it's just got the weight. It is like a well. And here you're looking, when we look at choice more generally than just ethics, right? Because ethics is a societal extraction of, or like a group extraction of something. It's how to coordinate such that you keep the most observers, the most of your group on the gradient while growing the amount of people you're sucking into the gradient. And because these things are all self-reinforcing, there's loops and cycles that either self-reinforce or they shrink. They go one of two ways until they reach sort of a new equilibrium or a dynamic equilibrium level. The better systems are the ones that pull in the more observers, because observers is the two of us compared to the 10 of us, we don't, or the 10 people on this call, we don't have the same computational power as 1, as 2, or as 10. We get access to different tools, different affordances from having the group, and that group level lets us play an entirely new set of choices that didn't exist in the individual. And so when you think about ethics computationally are like the coordination technology for more than one observer. And I don't know if you get, and this is some work that the ethics treatment is, at the moment, it's early. And so one of the things I want to explore on the ethics side is, well, is some version of this coupling dynamic, how observers couple and accept propositions and group, that informs ethics, is that working down? Is that working into cells in the same way? Is it just the same things, but with effectively more layers in us? Is it the same dynamic that you can work out that, oh, ethics is actually not just a human thing, it's actually a thing that is a function of how systems couple and how you form bigger observers. Like, these are one of the mechanics of it, and these are the rules of these mechanics. And so that's what I'm trying, because I think meta-ethics, it becomes very important today versus 5 years ago or 10 years ago, that we have these computational tools to start talking about these things. Yet most ethics discussions are still a philosopher typing into a markdown at Claude.ai, telling Claude, you're a very nice machine. And I don't think that that's particularly useful it's not robust enough for me when you're working on tools that can really change everything. And they are. I mean, like, the tooling today, even for work I do, just to be able to pull up the papers straight away that you've just mentioned and to have them read, these just for growing knowledge, it's already super powerful. So when it's integrated into everything we do, can we really live in a world where we have, you know, where we don't understand or can't interpret how these systems make decisions in a meaningful way? And so the work you're doing and the work your group's doing is like, I think, one of the critical legs of that, but it needs to kind of, pardon my pardon my language, but it needs to move out of the lab and into like the industry of it, because this is like, it's such a critical thing that, you know, the decision theoretic tools they have now to do this are not good enough. End of sentence. Like, it's just one of those things where we're sitting at this point where these ethical formulations start to have actual teeth. Like, it could be, you know, 5 years ago, it doesn't really matter if my theory of what the Ruliad and says, or computation says about ethics, is right or wrong. Now it's a start point to be improved on, to see if you can first do better, because I'm likely to have done it not so well, but also to see if we can do that because it's going to actually be useful instantly in the world, in something we're working on. So I think the work you guys do is super important for that.
Yeah, the reason I was showing this equation was because of its marked formal similarity with your path cost function. But it also allows me to speak to what you've just said. Well, let me just quickly unpack what I meant to imply by showing the two different decompositions of the underlying information gradient. No, it's not really. It's basically a cost. It's the action of the principle of least action. So it's a path integral of risk and ambiguity. And I just wanted to sort of again endorse and allowing you to sort of join the lexical dots, minimizing the expected the risk in an economic sense, just as minimizing the expected complexity, which just is complying with this importance of compressed representations. So, you know, and that was part of your cost function. Minimizing uncertainty can be read in a variety of ways, you know, by minimizing the entropy. You had entropy per se. This is a sort of conditional entropy, given what you can observe, sort of conditioned upon its causes. But you can rewrite that in terms of what in robotics is called intrinsic value, or intrinsic motivation, and extrinsic value. And the reason that this is, I think, a useful decomposition of this more universal objective function, which actually I should just say just is the mutual information that we were talking about, is that the bounded rationality you were talking about in terms of Bayesian decision theory all rests upon this, the expected log prior preferences or expected utility. But that's just half the Bayesian story. There's another aspect of Bayes optimality called the principles of optimum Bayesian design, which is asking the right questions, exploring in the right way the world, performing the right experiments that yield the content or the data that maximally resolves your uncertainty. And if you're in an ecosystem, or you're on a web of users, then that's uncertainty about somebody else. And this plays a really important role in terms of intrinsic motivation, optimal Bayesian design. And I think that this part here is exactly what you're talking about. That is missing from current AI and large language models. They're great at doing this in terms of predicting stuff, but they're not good at the moment at prompting themselves and being curious or trying to resolve uncertainty. So that's the sort of, you know, the story told through or using the language of, what's this one? Yeah, a similar story, just to sort of again endorse what you were just saying in terms of federated inference, belief sharing, co-constructing a common ground in which we can maximize our mutual information with others, inherits from putting lots of active inference agents together. So this paper basically shows that the emergence of a language and the endurance of phenotypes that can actually learn those languages it can be explained just by minimizing surprise or maximizing the expected surprise, read as when unpacked in terms of expected free energy, the mutual information that you were talking about. So if you're not aware of this work, I think you'll like it because it just shows, using a really simple toy example, that those memes and the language that you were referring to, the way that we communicate in a mutually informative fashion, is in and of itself a process of, can be read as a process of Bayesian model selection, where you're selecting those models that can learn from other models. So I thought you'd like that. Again, toy example, but sort of principled approach. Yeah. Now, I guess you've turned your microphone on because I can hear the ticking again. And now you've got off, so I'll assume you're just either gone to have a cup of coffee or just courteously listening.
No, I am listening. Apologies. I've just been trying to fix my mic for you. No, I guess one of the questions I had for you is just wanted to dig into your thoughts on sort of surprise and how it interacts with learning and structure, because you stated that surprise is sort of a minimization least path thing. Now, when you get, if in a toy model, if you get to an environment where all the learning's done and surprise is minimized for that agent, does the agent then have the resources for more exploration? Because I'm interested in sort of the dynamic between exploit and explore, because as a, animals less so than humans, when they run out of food in an area, they have to go and explore another area, even though it's going to be high surprise, because otherwise they die. But humans often, when we are stable and all our material needs are met, often produce lots of surprising things or seek surprise, which I just one of the things I wanted to understand is sort of how you think about that in the context of FEP, and just because it would be helpful for how I think about it in the context of observer theory, where I think that they must work together, or like we are agents that are different to other agents, because when we minimize surprise, we suddenly go, oh, we're going to get some more surprise now. That's sort of the dynamic I'm thinking about it.
Yeah, and I think that dynamic would be usefully in your sort of thesaurus writings, be unpacked in terms of a dialectic. So the dialectic, I think you need to resolve the questions that people naturally have about surprise minimization, is that in observing, in making sense of things, I am going to find the explanation that renders my observation, or at least the sensory consequences of the thing being observed, is as small as possible. This has got nothing to do with how I couple back and act upon the world. So coming right back to your original description of things that have this sort of reciprocal exchange between the observer and the observed. There's a two-way exchange. So the observed impresses its sensory impressions on the observer, but equally the observer in an inactive inference, and certainly in the physics and the free energy principle, also couples back to the observed. And that output is itself inferred in these deep structures. So in these deeply structured things, where the actual action, say the movement of muscles or autonomic reflexes, or the servo producing movement in a robot or a drone, that's so far removed from the actual computation that now the actual action now becomes planning as inference. And then we go, and planning as inference rests upon the expected free energy or the expected surprise. And we've just spoken, or we've just seen in that previous paper or graphic, that the expected free energy decomposes into an exploratory part and an exploitative part. The exploratory part is the expected information gain. That's the bit that complies with the principles of optional experimental design. And the exploitative part is the Bayesian decision theoretic part that's specified by a loss function or some prior preferences, or the, as you put it, the constraints. So the kind of thing that I am. So I'm going to always just be seeking information subject to the constraint. I don't surprise myself by finding myself on a branch on the Ruliad or in some part of state space that would render me not the kind of thing that I am. And that's interestingly, if you want to celebrate that dialectic by appeal to the neurobiology literature, Bayesian surprise is the KL divergence between your beliefs after and before making an observation. That means if you now treat from the point of view of observer theory, I think you need to make a crucial distinction between observation as something that is a passive sense making and observation as a verb, because to observe means you actually have to look somewhere. And if you're looking somewhere, you have to decide where to look. And if you decide where to look, one of the key motivations is called Bayesian surprise in the visual search literature. And Bayesian surprise is mathematically, this is another of your sort of lexical joining the dots. Bayesian surprise just is the expected information gain, which just is the intrinsic motivation, which just is the epistemic affordance, that just is the intrinsic value, which just adds so on and so forth. Everybody's got their own word for it.
Gosh, we're gonna have when I do this lexicography, it's gonna be like here's a sort of set of words on a whole A4 page, and then equals one word equals one sentence. I feel like it's gonna be that sort of paper. Here's 1,000 words.
But yeah, and I think that would be extremely useful. I mean, my suggestion here is that you could, if you want to talk about surprise, you don't have to. I mean, I can talk about surprise, I can talk about self-information. There are other words for exactly the same mathematical quantity. But if you like surprise, and you like to talk about observer theory, if you want to make it intuitive, then you can say there is surprise read as the implausibility of this sensory input being observed, given my predictions of it or my model of what caused this sensory input. But there's another kind of surprise that pertains to where I look, and that's the Bayesian surprise. And Bayesian surprise is good, because Bayesian surprise registers the expected information gain or the amount of uncertainty I could. So on the one hand, I'm sense making by minimizing surprise in the moment. On the other hand, I'm trying to maximize Bayesian surprise by being information seeking, by being curious, effectively, by being exploitative. And it'd be nice if you could link observer theory to sort of the layman's appreciation of what it is to observe. I'm just making the point that you can play on words, that observation is a very inactive thing. You have to look before you can at something, before you can get the data to make sense of it, in terms of saying, I have observed this. To observe, you have to choose what to observe. And that's how I think you resolve that dialectic. So surprise minimization is good for the sort of the inference. But the surprise maximization is good for what to actually do in terms of what you observe.
Well, I'm afraid, unfortunately, I've got to run. I've got a conference call in 5 minutes, so I've got to get back. I've got to get back to the day job. But guys, Carl and team, thank you so much for all the time, and I really appreciated speaking to you guys, and thank you very much for the great questions. And sorry for missing the last one. That was my fault. So apologies for wasting your time last time. But thank you very much. I really enjoyed it. And if you want to do any follow-ups and if you want any of the papers and stuff, just tell me. I'll drop you the links, and be lovely to work with you guys. And I'll try and I'll probably give Carl an email and be like, okay, give me all your words. I'm going to try and do a lexicography. Be fun.
Cool. Thank you so much, Sam, for the presentation. Really good.
Thanks,
And
guys.
thank you, Carl, as always, for your feedback. And thank you, everyone, for the questions and comments as well. Let's give a nice round of applause to Sam. Thank you so much.
Guys, have a great day, guys. Thank you. Bye.
Bye, everyone. See you next time.
Thank you. Bye-bye.